Welcome to this video on statistical mechanics. My name is Jos Thijssen and this video is part of a series I have made for my students in statistical physics, a class that I teach at the Technical University of Delft in the Netherlands. This video addresses the quantum statistics for identical particles, and in addition it calculates the canonical partition function, and the implications of the quantum statistics for particles when they get close are also addressed towards the end of the movie. I hope it's enjoyable and useful for students. This video is about the formulation of quantum statistical mechanics, and as usual, when we face a quantum problem we start by writing up the Hamiltonian. In fact, we don't specify the form of the Hamiltonian, but we just assume that it is an expression, an operator, which we can write as a function depending on the quantum numbers, the quantum operators corresponding to n indistinguishable particles. In order to analyze the effect of the indistinguishability, we introduce an operator Pij, which is a permutation operator. Well, in fact it's only an exchange operator. It exchanges particles I and j in the system, which means for the Hamiltonian that the quantum numbers of particle I and j are exchanged, and because the particles are indistinguishable, that should have no effect on the Hamiltonian. Formally, the Pij is defined by its action on a many-body wave function. So here we have a wave function psi, which depends on the quantum numbers of particles I and j. We call them xj. They may be the positions of these particles, but they may also include other variables like spin. And we see that the effect of Pij is to exchange the xj and the xi. Because the particles are considered to be indistinguishable, we should have that the commutator between the Pij, well, the Pij obviously is an operator, the h is also an operator. The commutator between these two should be 0, because Pij doesn't have any effect on the Hamiltonian. And we know from algebra that if two operators, let me put the hats on top of them, if two operators commute and they are both Hermitian, like is the case for the Pij and the h, then they should have simultaneous eigenstates, which means that there are eigenstates which are eigenstates of h, and simultaneously they are eigenstates of the Pij. The eigenvalues of h are usually denoted as E, that's the energy, and the eigenstates of Pij are just the eigenvalues of Pij's, we call them just lambda. And we have the following property for the Pij. If we apply it twice, we exchange I and j twice, so nothing changes in that case, and we are back at the unit operator. We haven't done anything if we exchange twice. Well, from this we can infer that, of course, acting with Pij squared on an eigenstate, then we get an eigenvalue lambda squared. And because the result of P is then itself the unit operator, the lambda squared should be 1. Furthermore, lambda should be real, because Pij is an emission operator, and therefore we can conclude that lambda is either +1 or -1. So we see that under exchange of two particles I and j, the eigenstates are either symmetric, that's when we have a +1, or antisymmetric, and that's when we have a -1. And in this context, the spin statistics theorem is extremely important. It is a theorem which was derived in the 30s by Pauli and other people, and I will not prove it here, but the conclusion is that half-integer spin particles, they always have lambda is -1, so they are antisymmetric, and we call them fermions. And particles with integer spin always have lambda as +1, and they are called bosons. For two particles the situation is rather simple. we have, for example, two particles with quantum numbers x1, x2. They are in a two-particle state psi, and we can write that as follows. This is just an example of a antisymmetric wave function. We have a 1 over square root of 2, and then we have particle 1 being in the state chi1. So please note the difference between the x1, that is the quantum numbers of particle 1, and this is the state the particle is in, so that's chi1. Particle 2 is in state chi2, and we have plus or minus particle 1 being in state 2 and particle 2 being in state 1. And because we have the plus and the minus sign here, it's easy to verify that the plus sign says that if I exchange particle 1 and 2, so I exchange 1 and 2, I have the same state. So that corresponds to lambda, the eigenvalue of that operation being plus 1. If there is a minus here, then the overall wave function changes sign, and that's the Fermion case, which I have up here. The next step is then to go to larger number of particles, arbitrary numbers of particles. Here we take n particles, and we can write the Fermion wave function as indicated by the f here, in the form of a so-called Slater determinant. So it's a kind of symbolic notation. The Slater determinant. So what we do is we take first a factor of 1 over n factorial square root, and that's just for normalization, and then we take particle 1 in state 1 up to particle 1 in state n, here particle 2 in state 1, particle 2 in state n, and so on until we have particle n in state 1 up to particle n in state n. So it should be correct. And so we work this out just as a determinant, and because if a determinant is antisymmetric whenever we change two columns, and that guarantees that this wave function is antisymmetric under particle exchange. Another way of writing this wave function is the following. We have the same prefactor for the normalization, and this is a sum over p, and p denotes any permutation of the numbers 1 up to n. So we sum over all the possible permutations, and we have then here this mysterious epsilon p, that's the sign of the permutation, and the sign depends on how many exchanges I have to perform in order to realize the full permutation. Any permutation can be constructed from particle swaps, and the number of these swaps can be odd or even. If it's odd, we take a minus 1 for the epsilon p, and if it's even, then the epsilon p is plus 1. And then we have the one particle wave functions, where the particles themselves are labeled just in the order 1, 2, 3 up to n, but the states the particles are in are permuted, so we have p1 up to pn. It would also be possible to swap this, to have the permutations acting on the x and not on the x on the chi states. That would just be chi1 up to chi-n. And it doesn't matter because we sum over every permutation anyhow. And so the end result would be the same. So the sign is plus or minus 1. And an important consequence of this form of the wave function is that we can have at most one particle per orbital, which is known as Powerless Principle. And the reason is that if there would be two particles in an orbital, so if an orbital would be doubly occupied, you would find that two columns in this determinant would be identical, and a determinant with two identical columns vanishes. So in that case we get 0. So we should have at least, at most, one particle in an orbital. An orbital can be empty, or it can contain one particle. It cannot contain two particles. So we have found a general form for a Fermion wave function, and you may ask now yourself, is it also possible to write up something similar for bosons? And the answer turns out to be yes. So comparing this expression for the Fermion wave function with this expression, we see Of course there should be a 1 over square root n factorial here. But if we sum here over all the permutations, and now we don't include the sign of the permutation, so each permutation occurs with the same sign, then it's obvious that this gives you a symmetric wave function. However, the normalization of this state is less trivial than in the case of the Fermion wave function. In the Fermion wave function, putting in 1 over square root of n factorial in front of it was enough to have a normalized state. That turns out not to be the case for bosons. For bosons, there may be more than one particle per orbital, and the normalization of this state is as follows. We get an n1 factorial, n2 factorial, etc., where the little n1 and n2, etc., they give you the occupation, they represent the occupation of orbital number 1, orbital number 2. Let us work out a simple example. As an example, we take two particles, 1 and 2, and they are both in the same state, which is chi. So the wave function then is x1 in chi and x2 in chi, and if these two orbitals are nicely normalized, then this is a symmetric normalized state. If we swap x1 and x2, we get the same state. But now let us try to follow the prescription here of the boson state for this case. Then we obtain the following. We have an x1 in chi. Obviously there should be a 1 over square root of 2 factorial in front. And we have x2 also in state chi. But we should have another term in which 1 and 2 are permuted, because we sum over all the permutations. x2 chi, x1 chi, and we see that both terms are the same, so we have a square root of 2 factorial and then x1 chi, x2 chi. So we are square root of 2 factorial of, and that's precisely what this formula says too, because this is the norm squared, and so in that case we would just have the square root of 2 factorial squared, which gives me 2 factorial. Up to now we have made frequent use of these one particle orbitals, which are called chi, and they can play a special role in the case where we have a non-interacting system. So for example, if we have a Hamiltonian, a quantum mechanical operator obviously, which is the sum of one particle Hamiltonians, which means that these particles are free because they have no interactions. And if we have such a case, then it turns out that the anti-symmetrized and symmetrized wave functions we have considered above are eigenfunctions of this Hamiltonian, provided that the chi-j's are eigenstates of the one particle Hamiltonian. So I take one of these little h's, they act just on one particle, and if the chi-j's are eigenstates of that, then all the linear combinations that we have seen above, the anti-symmetrized and the symmetrized product states and linear combinations of them, they are eigenstates of the total Hamiltonian. Now generally we are interested also in interacting particles, and so you may ask yourself, what's then the use of these chi orbitals? Well, if the Hamiltonian contains interactions, then obviously these wave functions, they are no longer eigenstates of that Hamiltonian. And the problem of an Hamiltonian with interactions is tremendously complicated, but often people use basis sets which which have the form like this, just as a basis in the Hilbert space, because the Hilbert space of particles, whether they interact or not, in many particle Hilbert space is the same for non-interacting and interacting particles. And so these wave functions we have just studied, they are used very frequently to express the physics. Let us now consider an example. The example is that of three particles which are in a finite volume, a box of size L times L times L, and the Hamiltonian is given in terms of, it's just the kinetic energy of the particles summed over all the particles. And we know the eigenstates of the single particle operator. That's this is a free particle kinetic energy, and the eigenstates are just plane waves, and a proper normalization tells me that I should put a factor of 1 over L to the power 3/2 in front. There is also an energy, an eigenvalue associated with these states, and that is h squared k squared over 2m. This is elementary quantum mechanics, so I assume that this is not really a problem. Now we want to calculate the partition function, and the partition function is defined as the trace of e to the power minus beta h, where h is the Hamiltonian operator. And the trace now is a rather delicate operation. We have here these eigenstates. They are the symmetrized or anti-symmetrized eigenstates, depending on whether we are talking about fermions, F, or bosons. So these guys are not simply k1 up to kn, particle 1 being in k1 and particle n being in kn. No, these are the symmetrized or anti-symmetrized states that we have seen above. And so these are sums over all the permutations, and in the case of fermions they get a sign for the permutation, and in the case of boson each permutation gets a +1, so there's no sign change there. Now it is extremely important to realize that we have to sum over all the permutations of the left state independently from the sum over permutations on the right state. So we will have an arbitrary permutation of the k's on the left side and an arbitrary permutation of states on the right side. But because the operator here is diagonal in the basis of the k's, we can conclude that in a permutation in the left state, the k for particle j, if that would be different from that in the right state, we obtain a 0. And the reason is that if we take the inner product between two different k's, states with different k vectors, that would give a 0, because the states are mutually orthogonal. So the only way to get a non-zero result is when the k's here in this permutation on the left hand side occur in exactly the same order as they occur in the right hand side. As soon as one k, if two k's are swapped on the left hand side with respect to the right hand side, then the result is 0, and that result follows from the fact that the Hamiltonian is completely diagonal in the k basis, and so the k should be the same on the left and right hand side. Here I have repeated that remark. The k's in the left and right state should occur in the same order. So mathematically you can express that as follows. If I have a certain series of k's here and you have k primes on the right hand side, there's a delta function for each j. The kj prime should be equal to the kj, and then the Hamiltonian, it just gives you the eigenvalues here, where I should add the j label with the k. Now, considering the definition of the Zn, we see that we should sum over all the k's, and it's then useful to replace a sum over k by an integral over k, and that involves an extra factor of the volume divided by 2 pi to the third, and the volume is obviously L to the third. L is the box length. So we can write now the partition function in this form, where we have 1 over n factorial d3k1 up to d3kn, and then this term. Now there is however one subtlety in the case of bosons. We have said that the k should be the same on the left and right hand side, but suppose that we have two k's which are themselves identical. In the case of fermions that's impossible, because it would mean that there are two occupied states which are the same, so two particles in the same state. But for the case of bosons, that is not unthinkable. That may occur. And so therefore we have to put extra combinatorial factors in the normalization. And if you recall correctly, we had looked at the normalization of the wave function that included this extra factor of n1 factorial and 2 factorial, which was the numbers of particles that I could put in a state. And it turns out that if I take care of all the permutations of the case where they are still the same on the left and right hand side, even if they are multiply occupied, that compensates precisely for this extra factor in the bosons. So if for bosons and fermions alike, this is the correct final result. And I can now evaluate this integral because it's just a Gaussian integral. It proceeds just as in the case of the classical partition function. And it turns out that it gives me a factor of lambda to the power 3n. And we see that the partition function is exactly the same as the classical partition function. So it seems as if the quantum nature of the indistinguishability of the particles is fully accounted for by this factor of 1 over n factorial, and there's nothing different apart from that. Well, it turns out that it is a little bit different, but in order to see that, we should have a look inside the system. Let's have a look at the two-particle reduced density matrix. So we have in principle a large system, but we integrate over the particles 3 up to n, and then we are left, of course, with a dependency on particle r1, r2, and here there may be different positions, but we take them the same. And this quantity tells me something about the probability to find particle 1 at r1, particle 2 at r2. And obviously here is my Boltzmann factor. So let's work that out. Now the difficulty is that here we have an r1, r2, and the Hamiltonian is formulated in terms of momenta or k factors. And so we have to insert a unit operator, which is of the form sum over k, k. This is the completeness relation in quantum mechanics, and we have to do that for particle 1 and for particle 2. So we have to include k1, k2, k1, k2 in this case. Here I have carried this out, so here we have the k1, k2, and here I have reversed them because on the left hand side we obviously should have a symmetric or anti-symmetric state depending on whether we are talking about bosons or fermions. And I have done the same on the right hand side, and I've properly reversed the states. So here we have rk and there it's kr. So this is the expression that we are required to evaluate. In order to do that, we should realize that this term has this form: k1 r1 are combined and k2 r2. And this one has a similar form, but the k1 talks to the r2 and vice versa. Working out then the expression gives me, for the term where the left and right hand side are identical, this and that one, gives me both a 1 over lambda to the power 6. And then we have two mixed terms, and these mixed terms, they involve an extra factor, e to the power ik1 r1 minus r2 and e to the power ik2, and then r2 minus r1, and these are dot products. And there is also the complex conjugate, because if we combine this term and that one, it is the complex conjugate of this one and that one. And if we work out the Gaussian integral, so you see this is nothing but a Gaussian integral because these are linear terms in the integration variables k, then we find the final result, where this would be, so if we would have just the classical ideal gas, the particles wouldn't feel each other, so I would just have a constant probability for two particles to be at two different positions. We see that this is the term which modifies this in quantum mechanics. And we see that if the r12 is, that's the distance between particle 1 and 2, if that is small, if it's typically smaller than lambda, you see that with the minus sign, the probability is reduced. So that means that the two particles don't want to be together, and that obviously corresponds to Fermion behavior. So the minus sign corresponds to fermions. The plus sign gives an enhanced probability for two particles to be close, and that's due to the boson statistics. Here is a plot of the three distributions. On the horizontal axis you see the interparticle distance. This is the probability to find particles there. Classically it's just a constant. For fermions it goes down, and for bosons it's increased for short particle separations. And the length scale over which this happens is, as you have seen before, the lambda, which is the thermal wavelength.